Hey team, I'm Maddie. Welcome to Science Say It Up. And today I am gonna learn, and maybe you can learn along with me, about a belief of flat earthers that to me is even weirder than the flat earth belief. And that is that they think uh light coming from the moon is cold and it cools the earth. So I recently learned that they think that, and I thought that it might be fun if we dug into a video about it. Um, ah, so I found one. Guys, here's the thing. I kind of like debunking flat earth stuff. But so often, let me show you. I've got the like playlist we're going to pull from pulled up here. Um, so often. So this is Mark Sargent's YouTube channel. And so this is his like proof the earth is flat thing. But like almost all of these videos are on um like taking photos, right? It's all about photography stuff. And I'm not a like the thing is that's not science, like and I'm not a photographer. I could talk about like light reflection and stuff, like basic optics. But to me, one that's kind of a decreasing returns kind of thing, because it was like, okay, and this specific, if we go like, okay, so let's take a look at Salton Sea Test 3 by Flat Reality, whatever, and we go and we see that look, we were able to take a picture of something further away than we should be able to given the curvature of the earth, right? Well, we know that there are processes that allow cameras and eyes to see further than you technically should be able to. It has to do with you can get it from like elevation matters, whether or not you're over water, because you can get like a reflection, so you can get like the signal you're receiving, right? And that signal, that's just light, right? That's just an optical thing. Um, that it's like bouncing off the water and coming back up, so you can actually see something that's further than the horizon. The more moist the air is affects things. And I don't know all of those details off the top of my head, and I'm not super interested in like figuring all of that out, because the whole idea of flat earth is nonsense. And here's my favorite. Listen to any flat earther out there. Hi, howdy, hello, I'm Maddie. I'm very nice, I promise. But if you could please explain to me how hurricanes form on a flat earth, that would be great. Because you need the Coriolis force to form a hurricane. You need it. This is also why hurricanes, on very rare occasion, but generally they can form just south of like 5 degrees, but 5 degrees latitude, like 5 degrees north and 5 degrees south, is a you know good rule of thumb threshold for how far away from the equator you have to be to form a hurricane. So you would need to explain to me in your because Coriolis is too weak, right? It's zero at the equator and gets stronger as you go towards the poles. Um, so you need to be able to explain to me how hurricanes form without Coriolis, right? If the Earth isn't a rotating sphere, why they don't form within that about plus or minus 5 degrees latitude, and you need to explain why northern hemisphere hurricanes rotate cyclonically, which is counterclockwise, and then southern hemisphere hurricanes rotate anticyclonically, which is clockwise. So you need that is explained by the sign of Coriolis flipping uh, when you switch hemispheres. But if there aren't hemispheres, then why is that? So like that's my challenge. That's my slam dunk on flat earthers. Make a hurricane, make a model, come up with a basic model, physics model of how a hurricane can form on a flat earth, and explain it to me, because I fully understand, and the scientific community fully understands why and how hurricanes form on a spherical Earth, or a mostly spherical Earth, or a geoid. Anyway, so if any flat earthers out there want to chat with me about that, we can totally go on a third party platform. I'm sure, like Debate Hub with Cheshire Vic, I'm sure she would be happy to host us. Or I'd be happy to go on any platform of your choosing, so long as it is a third party, right? And appropriately moderated. Yeah, so my email is just sciencesideUp@gmail.com. It's on my YouTube page. I'm easy to find, you know. Anyway, would love to chat about how that works, and specifically atmospheres, that like the atmospheric model that flat earthers think is real is not. And I can bring the data to show you. Anyway, okay. But so I was scrolling anyway, like sorry, that was a bit of a ramble. But I was scrolling through this playlist looking to see if there was something to debunk, and I saw that there is a real-time moonlight temperature test, and I had recently become like because sometimes I forget to go to incognito mode when I start searching conspiracy theory pseudoscience stuff. So sometimes algorithms recommend weird conspiracy stuff to me, such as like cold moonlight. And I finally put together that that's a flat earther belief. I almost said young earther belief. It could be. I don't know. But that's a flat earther belief. So that's fun. And then I also saw this video that says NASA flat earth climate change model. So that's cool. We might have to check that out depending on how long it takes us to get through this video. So without further ado, I say we check out this cold moonlight idea. And I don't have an ad blocker. I'm sorry. Okay.
Okay, here's a video a lot of people wanted me to make. Sounds really crazy. I'm using a FLIR, forward-looking infrared device, and it is an extremely clear night with a extremely bright full moon. There goes a car down the road. Huh? You can actually still see the brakes on my tires are a little warm there. So got a full moon and we've got a shadow. So let's do, in the light of the full moon, 16 degrees Fahrenheit, 16 degrees Fahrenheit, 13, 12, 12. Yeah, okay. Here we are in the shadow. You can't see the shadow, but I am absolutely pointing it in the shadow. 22 degrees average, 22, 21, 22. Let's go outside. 18, 19. This is in the moonlight. 20, 19, 19. Also in the moonlight over here. 17, 15, 14. And this is in the shadow right here. Here's the base of the shadow. The base of the shadow, of course, since the moon's been rising, is the spot, yeah, right here, 24, 23 degrees. I'll make sure I'm in the shadow. Yeah, there we go.
Okay, I just realized what we're looking at. Can you guys see my mouse? I don't know. Yes, okay, you can see my mouse. Okay, I think this structure here is a tree. And then that would be like a branch. And then this would be the ground beneath the tree. Cool. Cool. Okay, so hi team. Let's chat. Let's chat about what he's measuring. The moon isn't going to moonlight. Okay, sorry, let me back up a second. Okay, during the day, sunlight comes through our atmosphere. Our atmosphere is mostly transparent to the shortwave higher frequency wavelengths of the electromagnetic spectrum that are like at the peak emission of the sun. So for the most part, those sun's rays, that shortwave radiation, just blasts straight through our atmosphere and hits the ground. is then absorbed by the ground, um, by the Earth itself, and then the Earth then releases that energy. And so our atmosphere is heated from the bottom up, right? So it's not sunlight, it's not the shortwave radiation that warms our atmosphere, right? That warms the surface of the Earth, and then the Earth emits that. Okay. Um, so, so this is why the coldest part of the day, there's a spider, a very tiny spider right here. And he like, I'm sorry, I'm gonna squish him. Okay, he's squished. He must be the one that keeps trying to build webs on my mic stand. Possibly. Okay. We're not talking about spiders. We're talking about, oh, okay, the coldest part of the night. Check. So the coldest part of the day is like the hour or so before sunrise. Now, why might that be? Well, when the sun goes down, the Earth still has retained some of that day's energy, and it's going to continue to emit it after the sun goes down, right? And it's going to keep, there's nothing to do for it except it's going to keep emitting that energy, right? And by the end of the night, it's sort of, it's kind of tapped out, right? It's released most of the energy it absorbed during the day. Yeah. And so, and it's not receiving any more energy. So it's just like at that point, we've stopped. If you think of the Earth, think of it as a battery that the sun charges. Okay. So the sun, energy from the sun charges up the Earth with heat energy. And then, so there's kind of and then when the sun goes down, the Earth isn't receiving any more heat energy. It's just dissipating, continuously discharging the energy that it absorbed over the course of the day. So the coldest part of the day is going to be when the Earth itself is like the longest it has been since it received heat energy from the sun. Okay, then what is the hottest part of the day? Great question. The hottest part of the day is generally 2 to 3 hours after the sun has been directly overhead. So that should be 2 or 3 in the afternoon, as long as at noon the sun is directly overhead, right? Which it should be, but time zones are a thing. And so why is that? Well, it's because there is a time delay in this process. The Earth, it takes time for the Earth to absorb energy to charge up this battery and then release it. And that time delay, based off of like material properties of the Earth, is about 2 to 3 hours. You know, wishy-washy rule of thumb kind of thing. Okay, so now let's chat about the moon and moonlight. Okay, so the moon obviously doesn't produce its own light. It is both reflecting sunlight towards the Earth, and then also you can think of it as absorbing and re-emitting its own light. The light that it's going to absorb and re-emit is going to be at a much, much lower wavelength than sunlight. So it's at a very long wavelength. It should be at a longer wavelength. It is at a much longer wavelength than even what the Earth is going to emit. So the thermal properties of moonlight aren't going to affect the Earth. It's just not. We'll be able to see like the visible light that comes off of it. That's why we can see the moon, right? But those lower wavelengths where it should be peaking, those aren't going to make it through our atmosphere because our atmosphere is, translucent to those lower wavelengths. I'm very like I'm brushing past a lot of stuff. If you want more details about this, is called black body radiation. And I've got a whole video on the actual physics of that in my climate dynamics series. So if you're interested in that, that's cool. Okay. So the moonlight is not providing any heat energy to the Earth's surface, let alone cold light, which makes no sense whatsoever. It's not cooling it, I assure you. So if it's not cooling it, then what in the world are we seeing? Cool. So uh, what we're seeing here is the fact that different things will emit are so different objects, like a tree versus the ground versus pavement versus his car, are more or less efficient at absorbing and emitting the sunlight from the day, right? Uh so the tree is being picked up here as warm, right, on his camera. It's being picked up as warm because sorry, as of the time of recording, if you guys don't know, I am very pregnant and baby it just kicked. So it's very distracting when that happens, but also really happy. Anyway, hi sweetheart. I was probably leaning forward too hard. Because she doesn't like it when I lean forward, because then I think she gets squished, and I feel her a lot when I do that. So I'll try to lean back a little bit more and not squish the baby. Okay. Okay, what we're seeing here is really the efficiency, or the science term would be emissivity. So what we're seeing here is a reflection, is a representation of the emissivity of different materials. So, for example, let's just think about water versus land. I just noticed also that my mic stand is about to like pop out of itself. So let's hope this doesn't fall on me. Okay. Let's just think about water versus dirt or rock, right? Water is less efficient than land is at absorbing and releasing heat energy from the sun. Just heat energy in general. So this is why, right? If it's, hey, it's real hot outside, but you're on the beach or you're at the lake and the water is still cold, right? The water is significantly colder than the environment and it feels really good. That's one of the things that's going on, is that the land heats up faster than the water does. But then when the sun goes down, the land will also cool down faster than the water does. So water is better at retaining heat than like dirt and rocks are. Okay. And there's a lot of implications for weather from that and things like that, but that's just an example. So what we're seeing here in this just like still, right, is again, I think this is a tree, and then I think this would be like under the tree, which is what he's calling a shadow, if I'm like interpreting what he's saying correctly. Then what we're seeing is that, hey, look, this tree is more efficient at releasing stored heat energy than the ground. So the ground is going to hold on to that heat energy longer. Longer than the tree. It's going to release it more slowly over time. And I would love to see like side by side photos, you know what I mean? Like a daytime photo of what this actual setup is. So we like, cause I initially I thought that we might be looking at blacktop here. Cause blacktop, right, is going to absorb heat really fast and then be really hot throughout the day. And then once that sun sets, it's going to release that really fast too. So like right after sunset, the blacktop is going to be like have the biggest ping on an infrared camera because it's emitting the most energy. And remember that all of these things are going to roughly emit in the infrared range. So which is that's what this camera is picking up, right? It's giving you a measure of temperature, but really what these signals are is um, heat energy being released. So the brighter the color, the more energy being released. The cooler the colors, the more into those dark blues, the less infrared energy is being released. Okay, so that's what's going on. That's what's going on. And so also, for example, if his car engine was running, right, that would peak as really hot, right, because it's warmer because the engine is running. Anyway, so there's other things that go on other than just this clearly must be moonlight. Ooh. Okay. Let me make myself little again and we'll let him talk for a while longer.
19 degrees.
Okay. Oh, maybe that's a
18,
fence?
17.
Like
Also
a
in the
tree and a
moonlight.
fence.
So,
See,
there you go.
like this looks like a driveway to me, right? Or maybe this is a driveway and that's sidewalk, and maybe this back here is the road. And so, yeah, I would expect cement, sidewalk, driveway, roads. I would expect those to have that, like, that should be a higher emissivity. Please correct me in the comments if I just flipped those. I'm sorry, sometimes I flip things. Versus grass and foliage, right? These things are going to kind of retain their heat longer. So, for example, an intuitive way you can understand that ground traps heat, right? Is snow. Out here, down here in Oklahoma, when we rarely have consistent days below freezing, right? So it's hard for snow to stick because even though, say, today it is, excuse me, even though, say, today it's 25 degrees Fahrenheit outside, 3 days ago it was 50 degrees Fahrenheit outside. And the ground temperature is still above freezing even though the air temperature is less. So crazy fun things that can happen there. Okay, so yeah, so that can be, yeah, the ground temperature. Maybe anyway, hopefully that's a little more intuitive of like, oh, okay, yeah, the ground is going to retain some heat. Think about the conditions you need for snow to stick. Okay. Okay.
Opposite of sunlight, of course, moonlight is reflected sunlight, in case you didn't know. Obviously so, right? Right? Let's see. You still see the warmth of my car engine. Can you see it? Yeah.
And
Here's
there's
the
the warmth
neighbor's
of the
house.
house.
These are actually great for looking for.
Because the heater should be on, so the house should be relatively warm because we have that artificial warming thing.
Or heat leaks on the house. There you go.
Yeah, that's a good point.
Right at the base.
Like that's a thing that an infrared camera can show you where you're having heat leaks, and so we just very clearly saw in much cooler temperatures, right, in much the outline of the window. Okay.
To the house. Yeah,
There's a
there's
human
the
person.
reflection. Hey, waving at my reflection. There you go. So let me do this again over here while I'm standing in the shadow. Be super precise. Okay. I'm in the shadow. Am I in the shadow? No, I was not. There we go. Yeah, I am. 18, 19 degrees, 19 degrees, 19.7, 19.8. In the moonlight, 16 degrees, 15 degrees. Also in the moonlight, 17, 17.
So really to me, I'm just seeing, like, again, I don't know exactly what he's standing on. But I heard the crunch of leaves. And that pattern on the ground is maybe leaves. So like maybe what we're seeing here is like leaf covered ground, and then over here would be non-leaf covered ground. Like that would tell us a difference between these two regions, right? And so that would just be like, hey, look, dead leaves have a different emissivity than grass, right? Um, Okay, we'll let him finish. We'll let this video finish, and then I'll chat about a few things.
Well, what do you know? What do you know? Smack my butt and call me a biscuit, right? That's what they say in the South, deep South. I don't actually say that. Yeah, it's warmer in the shadow. Yes, absolutely no trickery going on here. It is an extremely bright moon out, and the sky is crystal clear. Warmer in the shadow. And this video is brought to you by Forward Looking Infrared, a FLIR. Thank you so much for watching. People.
Okay, so we can be done with that. Cool. Okay, so the other thing that I wanted to bring up about him was where he happens to be standing. We see that there's a temperature difference from this region, which is warmer colors, to this region. And he is saying that the only difference between those two regions is that this is in the moon's shadow and this is receiving direct moonlight. However, earlier in this video, let's get to a good frame. Like here. Okay, like this bit. Is this in shadow and this in moonlight, right? What's the difference between this point and this point? Or this point and over here, right? Is that's a very strange shadow pattern if that's what's going on. And so this is a thing to be careful of. So let's think about like some scientific thinking, right? We were just presented with a piece of evidence, right? Or with an observation. And the observation is, hey, after sundown, and in a full moon, I see two distinct regions of like warm and cold, or like lots of infrared emission and not lots of infrared emission in my yard, right? That's the observation. And that's a real observation. And so then we would want to then ask the question, well, what is causing that? And so his hypothesis is that the thing causing this is the difference between being in the under direct moonlight and under the shadow of the moon. So how could we test this hypothesis? Because this is where I often see flat earthers stop, right? They present their hypothesis as a conclusion. And that's not scientific thinking, right? That's not scientific thinking at all. If we have a hypothesis, we need to come up with a way to test it. So how could we test this hypothesis of, I think it is moonlight, right? This difference between moonlight and moon shadow. Okay, well, one thing we could do, we would want to set up a pretty controlled experiment. Maybe we do a box, and we figure out the position of the moon. We use GPS and all of that jazz, and we have two sides of the box, and one is covered, right, and one is open. And so we position it such that we're going to get direct moonlight into the open box, and then over the covered box, right? Obviously, no moonlight's going to get through, right? So we've made a shadow, and then we put the same material down underneath both spots, and we, have it set up, and then we take measurements like this, right? So we take like these like IR measurements, and see we even just measure the temperature. We just measure the temperature inside both sides of the box. So we could do that. We would need to also measure, measure the temperature in both of these boxes during different phases of the moon, right? So if his hypothesis is correct, then we should see a significant temperature difference between the moon shadow and the non-moon shadow, right? The covered box and the uncovered box. By the way, I'm designing this experiment off the top of my head, so bear with me. covered box and the uncovered box, we would expect the uncovered box to be colder than the covered box, and significantly colder, right? And we would have to understand what our significance level is there. Okay, so that would have to be like consistently greater than instrument error. Okay. Okay, so we do that. That would be if that happened, that would be evidence to support his hypothesis. We would also expect that if we repeated this experiment during different phases of the moon, that the temperature difference would lessen, right? So if we were at the new moon, so there's no moonlight in the sky whatsoever, we would expect the temperature in both boxes to be the same, right? And at say when the gosh, there's another spot. Is my office infested with baby spiders? I think it might be. I don't like that at all. Okay, because I killed. Oh, geez, I see like I can count like 3 more. My office is infested with baby spiders. Great, love that. I love that journey for me. Okay, well, let's wrap this up. Let's wrap this up so I cannot look at baby spiders anymore. Okay, cool. Okay, and then we would expect to say when the moon is at, if it's like half phase, a half moon, that would be, you know, we would still see a temperature difference, but it wouldn't be as great as that of the full moon, right? So that's what we could do. That's how we could test this hypothesis rigorously, fairly rigorously. But like, you know, you could do this for a science fair project if you wanted. I don't recommend doing it for a science fair project unless you have a child could do this setup. That's my point. But it still is a very valid experimental setup. Cool. And that's what he would need to do. That would be a great place to start, right? To test his hypothesis. And then do that and present the results and tell us what you find, right? And I bet what you're going to find is not the results you expected, right? And so when that happens, we would need to just reevaluate our hypothesis, right? And maybe fall back to the original observation. I see these regions with different temperature values after sunset and think about what else could cause that, right? Because that's what science is about. We can have wrong hypotheses. That's fine. I'm wrong all the time. Other people are wrong all the time. Science is about becoming less wrong together, right? So yeah. So anyway, that's this is something that I see a lot with flat earthers, especially, is they take an observation and draw the conclusion from that therefore the earth is flat without all of the steps in between, right? That's like I took a level on an airplane and it stayed level the whole time, therefore the earth is flat, you know? And that's like, no, man, your experimental setup there is flawed. The sensitivity of your instrument is insufficient, right? That would be my comment as a reviewer. So that's something that I see a lot with flat earthers in particular, is their experiments are really just observations. And so they jump from the observation to effectively a hypothesis. I see this. I think what's causing this is this explanation. But then they jump straight to, therefore my explanation is true because there exists this observation. That's not how that works. That's not how you do an experiment, right? We have our observation, we have our hypothesis, and then we would design an experiment to test that uniquely tests that hypothesis. Yeah. And then that will either support or not support our hypothesis. And we can draw conclusions and move on from there. Okay. Thank you guys so much for listening. I think we're going to stop here because because I am in a spider queen's nest, and I am would like to not be. Please and thank you. Cool. So I hope you guys are doing well. Thank you so much for sticking it out to the end of this video. You're cool. YouTube shill stuff. Like, subscribe, leave a comment. If you've got a question or a comment, or there's something I missed, leave a comment down below, and I'm pretty good at responding to those in a timely manner. Yeah, cool. All right, I will talk to you guys later. Okay, bye, team.